Now here, this equation actually represents, in the autocatalytic chemical reaction, the product, it says like, here's the rate of the chemical reaction. Doesn't it make sense that the rate would be a derivative? Because slope is a rate is a derivative, slope is a derivative. They're all the same thing. So they're telling me this is the rate of this chemical reaction, so it kind of makes sense that there's already a derivative here. In the next chapter, we'll learn how to go backwards and actually get the original equation. So they want to know, though, for what value of x will the rate of the chemical reaction be the greatest? Aren't they asking me for the maximum here? The rate of the what's the greatest rate that you're going to get? That would be a maximum, right? Okay. Lovely, lovely, lovely looking thing here. If this is already a rate and they want the maximum of the rate, I got to take the derivative again. I got to do basically the second derivative of this mess. Hopefully I can get through this math without messing up. They actually write it dx squared. No, they write d squared x. Okay. Okay. So let's think about it. Here's what I would do. You could use the product property here, but doesn't it look complicated enough? Right? Couldn't I just distribute and make a little easier problem for myself? I could say k times q naught times x, and then minus k x squared. I'd rather differentiate that, especially with all these coefficients that are variables. They just look kind of weird, don't they? So if I take if I distribute that and take the derivative, this isn't the second derivative. I've just rewritten the equation here. I shouldn't have put. It's the thing I don't like about working with this thing. I can't really erase. It's kind of clunky. That's not the derivative. All I've done is rewrite it, right? And again, I wish I hadn't even written it where I did, but squishing everything up here. So if I take the derivative of this, here's an x. Don't we usually just take the coefficient of the x? Right? When we take a derivative, if it was like 2x, we'd say the derivative is 2, right? So the derivative would be, of that term, would just be the coefficient k q naught. And then if I had an x squared, don't I usually take the 2, multiply it by what's out in front? If I do that, that would be minus 2k. And then it would be x, subtract 1 from the exponent would just be x to the first power, right? So this is my second derivative. So anytime I have a rate, if I want to maximize that rate, it doesn't matter if it's already a derivative of something. It's still its own little function, isn't it? No matter what I have there, if I want to find a maximum, I just go ahead and differentiate whatever's there. And if it was a derivative, I'm doing the second derivative at this point. So it's just kind of showing that here. It's still just one derivative for us, though. Now, how am I going to find, what do I do with that once I get it? What do I do with my derivative to find the maximum? I take the derivative and I what? Set it equal to 0. So I'm going to take this, and I'm going to set it equal to 0, and I'm going to solve for x. So here's the x. Here's what I'm going to do. It looks gross, but it's not too bad. You can move this term to the other side. Okay, and so that would leave me with kq naught is equal to 2kx. And again, remember, when I'm solving equations, aren't I just trying to get the x by itself? How would I do that here?
Divide by 2k.
Divide by 2k. Okay. So I've got x equal, hey, that fraction even reduces, doesn't it? Mm-hmm. The k's cancel out. And so q naught over 2 is going to be my maximum chemical rate, or my maximum reaction rate. So basically what this is saying is whatever the original amount of my substance that I had that I was doing this chemical, doing this reaction with, that I was using in this little experiment, if I split it in half, that's going to be my maximum. Because that just means Q naught was the original amount divided by 2. That just means split it in half and you'll have your maximum reaction rate there. Okay, so the math on that, on 19 on page 223, is a farmer plans to fence a rectangular pasture adjacent to a river. So there's a river. Maybe I should make it blue so you kind of can remember that is a river there. Would not work in central Texas. The river would dry up and the cows would get out. But if you had a rectangular plot, it would look something like that. And he said the pasture must contain 180,000 square meters. Now, I know that's an area because it's square meters, so they're talking about area there, even though he didn't say the word area in the book. Square meters, that's an area kind of measurement, so I know that you're talking about area here. He must have that much to provide enough grass for the herd. What dimensions would require the least amount of fencing? So we want the least fencing that you'd need since he's building this on the river. The least amount of something would be the minimum. Okay? So whatever it is, minimum is still a critical point, right? When we're talking about fencing, what kind of idea is that here? It's not an area. What is it?
Perimeter.
It's a perimeter. Good. Okay, so we're going to write an equation for perimeter. Now, if it's perimeter, let's see, whatever this is here, let's say this is x. Wish I could get this. I can't write on this thing very well. Let's call these y values because you can almost imagine putting this on a coordinate point, right? A coordinate grid, and kind of thinking about it that way. Wouldn't it be x plus 2y because you've already got one of your sides. So normally perimeter is like 2x plus 2y on a rectangle, but you've got one side already, so you just need x plus 2y here for your fencing. Okay, now what am I going to do? How am I going to differentiate that? Because that's what I need to differentiate in order to find the minimum amount of fencing, because fencing and perimeter are the same sort of ideas. What else do I have to work with? Well, I have this over here. I have this area, don't I? Now, what do I know about the area of this thing? How could I write an equation for it? It's equal to 180,000. But wouldn't the area still just be x times y, length times width, right? Okay, so it's still the same, even though they don't have that side, that fence there. So if I want to differentiate the perimeter, the problem that I have over here, which we're going to solve in the next chapter also, actually the next section that we cover, is that I got two variables, and I don't know how to deal with that so well. Actually, I've got the function over here, and then I've got x plus 2y. If I could get rid of that one of the variables, it would help me a little bit, wouldn't it? Why don't I solve for, let me get rid of my y. If I've got this equation here, couldn't I divide both sides by x and say that y is really just equal to 180,000 divided by x? I could stick that over here is what I'm going to do with it. And this is what you see in some of these problems too. It's something that you see happening a lot. I could say, okay, well, y is really just 180,000 divided by x, and that way I only have one variable going on here. I'm going to call this P of x for perimeter, okay? By the way, your book, when you go look at the answer key on some of this stuff, they call everything S for some reason. So just kind of know, if you don't like it, just, do your own thing. Let's go ahead and simplify this. This is P of x is equal to x plus, that's what, 360,000. And couldn't I write this as x to the minus 1 power just to move it all up? Because what I'm wanting to do is use I can't even remember the name of the rule now, but the easy differentiation, you know what I'm saying? So if I want to minimize, if I want to find my critical points, I'd say, okay, well, the derivative of x is 1. And the derivative of 360,000, I forgot a zero, x to the minus 1 would be minus 360,000 x to the minus 2. Let's think about how I might want to write that. And it might work nice to differentiate, but if I'm going to set this equal to 0, it might not look so great. Isn't that just 360,000 over x squared? Right?
Yeah.
Are you following that okay? Okay. So now I'm going to go to a new page because that's my derivative, and now I got to set it equal to 0. So I'm going to set the derivative equal to 0, and it was 1 minus 360,000 over x squared. Right? Here's what I could do. I don't know if y'all, from algebra, y'all got any ideas here? What I'm going to do is going to end up with the same result, but I'm just going to say, well, since that's a minus, I could even move this one to the other side. Blah, 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 over x squared. Add it to both sides. And then I wouldn't even have to, it doesn't really matter. It's both the same thing, isn't it? I'd have 360,000 over x squared is equal to 1. You remember what you would do next to try to solve this? Well, you could multiply both sides by x squared and get the x's on one side. One nice little trick is, remember, if you have a fraction in math and you want to get rid of it and you got just a whole number or even another fraction on the other side, remember you can cross multiply. You can turn 1 into 1 over 1 and cross multiply and say 1 times x squared is x squared, and 1 times 360, whatever, I can't say that number, 360,000 is that. And now it's easy to solve, isn't it? We just square root both sides. So x is the square root of 360,000. Okay, so we've got x is 600. Well, x is 600. That tells me, if I'm thinking about my diagram that I drew, remember the river was up here. This was x, this was y. But they asked me for the dimensions that would give me the least amount of fencing. Okay, so I'm only getting one critical number. This must be the minimum amount here. And what I can do is I can actually go put that original equation where I changed it to all x's. I could put it in my calculator and look at it, and I could look at the table. But this is going to be the smallest amount of fencing that we want. We took our maximum amount of fencing, and I can do some crazy stuff with that, but that's not really a reasonable idea here in this problem. It's not like I want to make a 0.1 width thing and stretch the fencing out as long as I can get. So in this problem, even though we have one answer, we're going to know it's our minimum because the other idea doesn't really make sense with what's going on here. If x is 600, remember we had the equation, the area is equal to x times y, and we knew that was 180,000. So if I want to know, if I know that x is 600, 600y is equal to 180,000, divide both sides by 600, 6 goes into 18 3 times. I have 4 zeros and taking out 2. It should be 300, I think. Is 600 times 300 that number? Yeah, it is. So my dimensions would be the 600 that I found from solving the first derivative set equal to 0. And then when I plugged it in, I could find the other dimension was 300.